Hello everyone and welcome to this lecture on multiple stage amplifiers. The outline for today's lecture will be the following. First, I'm going to talk about why multiple stage amplifiers are needed in analog integrated circuit design. Then I'm going to talk about noise considerations, linearity considerations, and then speed or bandwidth considerations. Then we're going to move towards how we implement the nullor with the multiple stage amplifier. And probably the most important part of today's lecture is how to do frequency compensation. And finally, we will run a big examples that shows how the compensation techniques work. As we have seen until now, single stage negative feedback amplifiers provide rather poor loop gain and actually loop gain product with the pulse. So the main issue is that we cannot get very good accuracy with a single stage, and then we also have limited bandwidth and linearity. The main problem is that a single stage is responsible for low noise, responsible for handling the load, and responsible for giving enough bandwidth. So there are just too many tasks for a single amplifier stage. So much better performance can be achieved by building our nullor with a different stage, so that we can separate the problem of noise and nonlinearity. And as we saw before in lecture on noise, it is actually the input stage, the ones that dominate with noise, that we can optimize this stage for noise. The output stage, we saw in the lecture of linearity, that is the one that is mostly responsible for the nonlinearity in the whole amplifier. So we optimize the output stage for linearity. And these are, of course, we separate these problems. So these are positive things. This is positive, this is positive. Now, the problem that we have when we are adding stages is that they are also coming with poles and also zeros. And then the contribution with poles raises the problem of instability. So we have to check for stability, and very often, most of the time, we will have to apply some techniques for stabilizing our amplifiers. So let's review very quickly the noise optimization. So we are talking about the input stage in an amplifier. So our strategy for noise optimization will be to first select the feedback network, those passive components, if we are using a passive feedback network, that do not deteriorate the noise that it is already coming in the source. So that will be our target, the selection of that feedback network. Yeah. And then for the implementation of the nullor, it is actually the input stage that dominates the noise performance. So we will have to put a lot of work on this one. For the input stage, we can select, depending on the type of amplifier or the implementation, as we will see very soon, we might need a single or differential input. And we have talked about different stages that can be used. The common source stage and the common drain and common gate stage have better noise performance than the other local feedback stages, like the series or the shunt. So we shouldn't use series or shunt stages as input stages. Then from these three stages, the common drain and common gate have one parameter that it is around 1. So it is a voltage gain or the current gain is equal to 1, and therefore they are inferior in noise performance than the common source stage. So whenever possible, we should use the common source stage as an input stage in a negative feedback amplifier. Then when we have selected already the stage, then we do the optimization. For that, first we extract an analytical expression. So we extract an equation for the input referred noise power spectral density. We can integrate it over the band of interest and do optimization. That optimization, it is basically finding the right sizes and bias of the transistor so that it accomplishes the noise specifications. For that, we have very nice tools that are going to help us, mainly the GM over ID method, in which we have FT curves, IDS curves, and also intrinsic gain curves at different current levels. So with those tools, we can find the sizes and bias of the input transistor. On the other hand, for linearity, now we are talking about the output stage. It is actually the last stage, the output stage, the one that defines the distortion and signal handling. We defined the figure of merit for distortion, that it is the distortion divided by the gain of each stage, so the contribution of distortion and the contribution of gain. So when we divide it, we get this figure of merit that tells us how good our stage is in comparison to other. And we found that the common source stage and the common drain and common gate stages can be used, but the same as with the noise, so other stages like the shunt stage or like the series stage should not be used as output. So we might think sometimes that applying local feedback in some stage improves the total linearity. That is not really true. It also reduces a lot the gain, so we shouldn't use local feedback stages as output stage. Now we have that the common drain and common gate stages have one parameter that is equal to 1, and therefore they must handle both at the input and the output the same current or voltage depending on this common drain or common gate. That means that there will be large voltage swings at the inputs and at the outputs, and they behave because of this. They behave they underperform the common source stage, in which only the output has a large signal swing. So whenever possible, we should use only common source stages as the output. Now, the output should be able to drive the load, and actually the feedback also is load and the feedback. And we will always have requirements from voltage swing and current. So we will have these requirements. So we will have to decide what is the biasing, the optimum biasing for the output stage, so that it can drive the load without the clipping. And that is basically the main task when we are designing the output stage. Getting to these voltage values and current values that are required to keep the transistor in the linear amplification and not in clipping. Now, there is another detail that it is also important, actually a couple of details also, is that the stage driving the output stage might also introduce nonlinearity, and that is particularly true if we use common drains and common gate stages. As I mentioned before, the output voltage or current is the same as the output, approximately the same as the output and at the input. Then driving the output of the intermediate stage or the input stage also very hard. So we need to check very carefully the stage that it is driving the output stage, so that it doesn't enter in a nonlinear situation. This might also happen due to slew rate. So we have to be careful when we have large capacitors inside the amplifier, inside the Nuller, in particular due to stabilization reasons, because yeah, we might end up in slowing problems. Okay, so that is the distortion optimization. Now, the design considerations for bandwidth. We have that we have really good arguments for using the common source stage both at the input and at the output of the amplifier. It has to be used as much as possible. So we have that we have a lot of amplification. Yeah, ABCD of the common source is much better than in the other stages. So we have a larger loop gain pole products that help us for the accuracy. We have much better linearity for the same reason that we have a lot of gain. It is corrected. A lot of loop gain. The nonlinearities are corrected, so we have better linearity. However, there are some very important issues with the common source stage. One is that it is just an inverting configuration, so the input voltage gets inverted at the output, and sometimes we need to invert it again. The differential configuration solves this problem because we can select which output to take, positive or negative. So we can solve it with the use of differential configuration. The only problem is that there is no offset cancellation. So what it means that it's not offset cancellation, the output, it is always superimposed to the VDS of the transistor. We have seen that using the differential stage, these offsets and also the even order distortion is removed. So the use of differential configuration can alleviate this. Now the next one is that there is a poor designability due to the CGD, and this is a serious issue. As we saw before, the capacitor CGD introduced several design challenges. So introduce a right-hand 0 in the transfer function. It introduces also pole splitting. It provides also Miller effect. It introduces Miller effect. And something that it is also very interesting is that even though this capacitor CGD is an overlap capacitance, that it is very linear by definition, the moment that we multiply by the gain in order to find the total Miller capacitance, it becomes very non-linear because the transconductance of the amplifier and maybe the output resistance as well might be non-linear. So the nonlinearities of the amplification get actually amplified by the Miller effect. So this capacitance becomes very nonlinear. Now these issues can be at some extent mitigated by using a cascode configuration, as we saw before. The cascode isolates very nicely CGD, so it is not connected from the input to the output, but just to the intermediate node, or also using the long tail pair. Now we have different building blocks that we have studied, and we have the OR transistor as a ABCD or as a two-port model. We have the following for the OR MOS transistor. That will be an MOS. The PMOS is exactly the same, so the same model, two-port model. So we are just going to assume that our CMOS transistor has the following symbol when we are building our multiple stage amplifier. Now, the basic configurations that we can have and their small signal models are the following. We have first the one for the common source amplifier. that it is just a transistor. We have the two-port model, and then we have the small signal model here on the right. So this will be the small signal model for the transistor connected as a common source. And we have already been using this before. Then we found a model for the cascode that it is here, and that will be using this model for the cascode configuration. We have a model also for the differential pair here. So we have model for differential pair. We have also a model for the differential pair with a current mirror load that it is very common also. So we have a model for that one here. Note the difference in the differential pair. We have half of the transconductance working, and on the other hand, here we have the whole transconductance working due to the current mirror effect. And we have also the long tail pair here. Okay, so those are the basic building blocks that we will be using during the implementation of multiple stage feedback amplifiers. Now let's take a look at a couple of examples. Yeah? So for a voltage amplifier, we have our asymptotic model here, and then we need to implement the nuller. So one alternative will be to use a differential pair, and that is how we connect the differential pair here. Okay, we connect the differential pair, and we have that one of the outputs will be grounded. So this is one alternative, and as we mentioned before, single stage, we use a single stage block. We use the differential pair as if it were a single stage block, even though it has two transistors. So this is our model as a single stage block. It doesn't have very large loop gain. It's a single stage, so we might want to put another stage to improve the loop gain pole product, and we can add, for instance, a common source stage. So if we add one transistor, it will look like this. So we will have the following connection, and note how I am piling up. So this is going to be the two-port network 1, and then the second network. So if I draw my nuller like this, I have to connect the output port of one network to the input port of the next one, and so on. So that is necessary, so otherwise my models are not valid. So that is important that is a very important detail. So the output port of one stage has to be connected at the input port of the next one. I have another alternative is to use the current mirror that we have discussed before. Differential stage with a current mirror. And then this one we deal with this one as it were a single stage, as I mentioned before. We have a model for this one, even though it has at least two amplifying stages and the mirror that is also can consider be an amplifier with a current gain of 1. So in conclusion, there might be different ways to implement the nuller, depending on how we use the basic building blocks. Depending on the requirements, we might need to use cascodes to improve the loop gain at low frequencies. We might need to use different different stages. We have another example here, the current amplifier. So on the current amplifier we have one terminal connected to ground and the other terminal connected to the feedback network, and then that can be implemented with common source transistor at the input and a differential pair at the output. We could have also done this in the opposite. We could have put a differential pair at the input and a common source at the output. So note something that is interesting here. The output, both outputs are floating, and so we have both outputs floating here. Okay, we will have an example of current amplifying design in the last module. Okay, so we go forward. We have that something also that it is very important is that we can have different feedback loops, and most of the time in this course we are designing an amplifier with a single loop, but we can also have situations in which you have multiple feedback loops. For instance, in this first example here, in this one we have that we are fixing both the transconductance and the transimpedance in this configuration, and that allows me to do very interesting things. One interesting thing about this is that if I fix these two parameters, I can create an input impedance. I can generate that particular input impedance. So we have that the input impedance is the input voltage divided by the input current, and we have that the output is equal to the output voltage divided. It has to be equal to the output load that I have is equal to the V out divided by out. So when I replace these equations and divide this one divided by this one, I get a very interesting expression, meaning that I can create the input impedance that I want. This can be useful, for instance, in applications in which we have to terminate an impedance. Something that comes to my mind directly is, for instance, in radio applications where you have transmission lines and connections to filters or antennas, so they need to be terminated at a very specific impedance. So we can generate this impedance by placing the right ABCD values. Another example that I have here, and it is very common, is, for instance, this one here. Is now we have an amplifier, and then we have the first amplifier here, like the one that we just discussed, and then we connect the buffer here to isolate this node from the output that can, for instance, be a very small resistance, and then it needs to be isolated so that it doesn't affect the gain of the first stage. And there is nothing particularly wrong about this connection. However, it can be improved a lot. If instead we connect instead of connecting the impedance RF to the output of the first stage, we can connect it actually to the second amplifier stage. This is an overall loop. This overall loop, it is much better because now we have the gain of both amplifiers contributing to the loop gain of the whole circuit. So in this case, this is just one loop gain here and the other loop gain here. But now we have much more loop gain because now both amplifiers are being connected in a single loop. So we have included overall feedback, but now think, we have also the issue that we have a multiple feedback loop. Here we have another common example. We have a transconductor that converts the voltage into current, and we have this voltage here, it is converted into current, and this current, it is flowing in this direction, and then it is converted into voltage here. Again, we have this amplifier and this amplifier, basically they are separated. It is possible sometimes to connect this feedback resistor directly to this node instead, and then you get that both amplifiers contribute to the loop gain of the whole circuit. So we have overall feedback, so it improves the loop gain pole product. Okay, so we have seen that we can build a nullor using different stages. Now, as I mentioned before, each stage will add at least one pole to our system, and then we need to check if we are able to achieve the requirement bandwidth, that it is always a specification when we design an amplifier. So we come back to the analysis that we did in a previous lecture on feedback, and then we found out that the achievable bandwidth in a negative feedback system, it is related to the loop gain and pole product that we have here, and the achievable bandwidth assuming that we can move the poles to Butterworth positions can be calculated like this. Okay, so you have n poles, and then we can move the n poles to Butterworth positions, that it is the maximum bandwidth that I can achieve. Then it will be the n root of the loop gain pole product. Now let's study this expression for a second. We can see that the available bandwidth, it is related to the loop gain. I mean, normally the loop gain, it is larger than 1, so we can just omit this 1 here, and then we see that the loop gain should be as large as possible. Okay, so that is one of the things that we should try to maximize the loop gain, because then that is the thing that is going to move the poles to higher frequencies. And the second is that these poles here, they have to be moved somehow to the Butterworth positions in order to get the maximal bandwidth. And we will have to do that using compensation techniques. And we have also discussed a little bit about how to manipulate the position of the poles, and we introduced before the concept of the phantom zeros. So the phantom zeros, when they are added, the phantom zeros will attract the position of the poles to them, and if we put these zeros wisely, we can place our poles in Butterworth positions or close to Butterworth positions. If we can put these zeros we can place these phantom zeros in positions that allow me to manipulate these poles. Not always possible, but very often we can introduce these phantom zeros and that do a very good job. How we can do this in our circuits? Well, there are a few ways to introduce these phantom zeros. One way is to add series or shunt impedances at the input. So we talk about that every pole in the asymptotic gain becomes a 0 in the loop gain. So we will be searching of ways of introducing poles in the asymptotic gain, and one way it is to introduce series or shunt impedances at the input. Now, as we saw before during the noise lecture, every series or shunt impedance at the input deteriorates the noise performance. So we have to be careful with that. So it is not our first choice to introduce series or shunt impedances at the input. Another alternative it is adding series or shunt impedances at the output, but as we also saw during the linearity lecture, adding impedances at the output deteriorate the linearity. Okay, so it's not going to be our first choice either. But we have another alternative. It is modifying the feedback network. So if we can introduce the poles in the asymptotic gain by modifying the feedback network, then that will be actually our first choice. Now again, let's revise something that we have already discussed. Forcing the poles of the of the closed loop gain means into Butterworth positions means that we need to make the achievable bandwidth that we calculated equal to the WN squared, that it is the maximum bandwidth in a Butterworth filter. And typically this factor is going to be much larger than 1, so we can omit this one. And then we have at that the loop gain pole product is going to be approximately this, and for 2 poles that will be square root of 2. The square root of the loop gain pole product, it is going to be equal to the maximum bandwidth that I can achieve. Okay, so we can achieve this bandwidth, but we have to check if it is actually possible to do that. Another condition for this is that P1 plus P2 and the loop gain divided by the 0 has to be equal to P1 plus P2 plus WN squared divided by zeta in the Butterworth filter. And this has to be equal to minus the square root of 2WN. So this is in the Butterworth filter. So with this equation, we can see that the position of the phantom 0 is equal to minus the achievable bandwidth divided by P1 plus P2 divided by plus the square root of 2 omega n, and this is for 2 poles. This equation is valid for 2 poles. Typically we will be handling around 2 dominant poles, and in some particular cases up to 3 poles. Larger number of poles are very difficult to manipulate. Now very important to notice, P1 and P2 are negative. Okay, so this is important. For the 0 to remain in the left hand side of part of the complex plane, we need that this has to be accomplished. P1 plus P2 absolute value has to be smaller than square root of omega n. So when this is achieved, it means that we can create a 0 that move the poles to the Butterworth positions. but we have to check this one. If this is not possible, it might be that one of the poles that we have here, it is not really dominant pole. So we are not able to move that pole in the butterworth position. So we have to double check that it is possible. Okay, and how to do that in the circuit? Well, it depends on the amplifier topology. So we have a voltage amplifier here, and then we have, if the impedances are resistive, then we can introduce a pole in the transfer function, in the asymptotic gain, by placing a capacitor here. Okay, and that will introduce a pole in the asymptotic gain, and that pole will become a zero. That will become a phantom zero. Okay, so this is one alternative. We have that if the impedances are capacitive, then a pole in the asymptotic gain can be created by inserting a resistor in series. So then, if this is a capacitor and this is a capacitor, then I can introduce a resistor here, air compensation, in order to create a pole in the asymptotic gain, and that will become a zero in the loop gain. So these are the two ways to create poles in the asymptotic gain. We will see in our example, we have the voltage amplifier with the resistive feedback. We will introduce a phantom zero. In transconductors amplifiers, we have if zeta 1 is resistive, so if this is a resistor, then a pole in the asymptotic gain can be created by introducing an inductor. And this is a tricky one because we really don't introduce inductors in integrated circuit design, only at very high frequencies. So this is not very easy to implement. In the transimpedance amplifier, we have that if the feedback is resistive, we can introduce a capacitor here. We introduce a capacitor here, and then we create a pole in the asymptotic gain that will be zero in the loop gain. If this impedance is inductive, then we will need to put a shunt resistor instead. In current amplifiers, if the impedances are resistive in the feedback, then a pole in the asymptotic gain can be introduced by adding a capacitor in parallel to zeta 1. So it will be here. We introduce a capacitor in parallel to zeta 1, and that will create a pole in the asymptotic gain that will become zero in the loop gain. And we will see in the last module we have a current amplifier similar to this one here. We will be introducing this for compensation. We'll see an example of this. If the feedback is capacitive instead, we will need to be inserting resistor in series to, if these two are capacitive and this capacitive, we will be needing to insert a resistor here in order to create this pole in the asymptotic gain. So we have a very easy methods to create these phantom zeros just by introducing capacitors or resistances in the feedback network. Okay. Sometimes we have the situation in which the application of the phantom zero does not work. So it's not that it works for any all the cases. It works in many cases, but in some cases we cannot move the poles to stable positions just by using phantom zero, and then we have to resort to other compensation techniques. One that it is very popular is pole splitting, that basically consists of adding a capacitor and a resistor in series that are connected in series in the middle of a common source stage somewhere in our amplifier, typically in the second stage. So the method works like this. So let's think for a second that we don't have any compensation here, and then we will have one pole that it is coming, for instance, from the input stage, and the other pole that it is coming from the output stage. So we will have these two poles here. Which one comes first will depend on the resistors and capacitances, so we cannot predict exactly where they are. But let's go into assume that the first pole, the one that we have called P1, it is coming from here, and P2, it is coming from here. Okay, so we have P1 and P2, and now, without any compensation, the location of the poles are as it is shown here. Then if we add a capacitance here, we add a C-split here, we will have this pole splitting. Then we will have two things that happen. First, we will have there is a Miller effect, and due to Miller effect, the load that we have, the capacitive load that we have in this node, will increase. So that will be approximately equal to CGS C split 1 plus GM RDS in parallel to RL. This is one thing that will happen. Now, if the series resistance here, the series resistance, it is very large, we will have something else entering in this equation. If it is very large, that I can assume that the model for my circuit will look like this. And let's take it only the resistor. So there will be GM times VGS, C split, and then the capacitance here, CGS. So if this resistance it is quite large, I can just disregard it, and then we have a very interesting situation happening here. As we studied before, this structure will behave like a resistance. So that resistance will be around 1 over GM multiplied by, and then we have C split plus CGS, then divided by C split. Yeah, so the larger that we have the capacitor connecting the gate and the drain, the larger the influence of 1 over GM here. And 1 over GM is typically much lower than RDS and RL. So actually we will have to put this in parallel to 1 over GM, and then that will be C split plus CGS divided by C split. Okay, so The first pole will move. The first pole will move to a lower frequency. Will move to a lower frequency. That means it goes in this direction. So it will arrive here to the new position after C split. And the second pole, due to the reduction, also the reduction in impedance at the output, the second pole will go to -1 divided 1 to P, and then we have all the output resistance RDS in parallel to RL. Now that will be in parallel to 1 over GM, and then we have C split plus CGS divided by C split. So these are only the resistances, and then all the capacitance at the output. So we will have, in this case, the load that also contains all CDS, but there is also another capacitance here. So now we see the impedance here, we will have also this capacitance that appears here. So that capacitance will be C split times CGS divided by C split plus CGS. And then depending on the values of these capacitance, they might not really change much. Then CL might dominate, but this one, it is very important, this part here. Okay, this part here is very important because it reduces a lot the output impedance. It may reduce a lot and then reduce the output impedance, and it sends this node to a higher frequency. So it end up here. So the pole 1, it has been moved to a lower frequency, and pole 2 to a higher frequency. Okay, so that is the effect of pole splitting. But then the third step here is that we can add this resistance. And then when we add this resistance, we introduce a 0 in the transfer function. And this 0 takes this value. And it is very interesting because in this value, depending on my resistor, I can move this 0 to from the right hand plane to the left hand plane. So I have the possibility of move this 0 wherever I want, depending on the value of the resistor. Now, one thing that I can do, it is basically to move it at very high frequencies where it doesn't affect me. Or I can do something very smart, and it is to place this theta 1 over the second pole. So if I put it over the second pole, it will cancel it. So I will try to put my 0 here over the second pole so that it will cancel the second pole. Yeah. But when I add the resistor, I will have also that I have introduced another pole, but it is a bit higher frequencies. So that since it happens at much higher frequencies, it interacts much less with the P1 and gets the circuit much more stable. The next compensation technique that we are going to study is pole zero compensation. And this technique, it is kind of similar to the Miller compensation that we saw before, but instead of connecting the capacitor and the resistance between the gate and drain of the transistor, we just put this series connection between the gate and ground, so we don't add this interaction between the input and the output. On the other hand, when we do this, we don't have the capacitance multiplication, the Miller capacitance, so that moves the pole very quickly to a lower frequency. So we will be needing a much larger C-split in order to achieve the same result as with the Miller capacitance. So there is no Miller effect here. So the position of the pole, we take again the first pole at the input. We have that the first pole we move to a lower frequency, P1 here after C-split, and it will take this value here. And if we add a resistance to this capacitor split and R split, we will also be adding a 0, and the position of this 0 is this one here. Now, depending on the value of this resistance, we can put this 0 in a particular place, and then we will be selecting to put this 0 precisely over the second pole. So when we do that, we do pole 0 compensation, pole 0 cancellation here. Okay, so this pole will disappear, but we will be adding another pole. So the third pole will appear around 1 minus 2 pi, and then we see the circuit. Since C-split will be a large circuit, a very large capacitor, it will short circuit this at relatively high frequencies, and then what we will have left, it is these two resistors here that will be producing a pole. So that will be R split times CGS. So that will be the position of this third pole, but this pole will be at a much higher frequency. So it will be a higher frequency there, and then we can see here that the poles are at larger distances, and they have less interaction and less effect on the stability. Now again, C-split it is much larger because there is no Miller effect like we had before. Here we have a Miller effect, so small capacitance here, or relatively small capacitance, will move the pole very fast to a lower frequency. Here we don't have that, so we will have to use a very large capacitor for the same effect. So this technique is not amenable for chip integration because the area of the capacitors are very, very large, and they become very expensive. The next technique, it is resistive broadbanding, and the main idea here is that we can change the position of one pole in the transfer function just by adding a resistance. And the main idea here is that without the resistance, we will have that there is a pole at low frequencies. After I add the resistance, I reduce the gain at that node, but I will increase the bandwidth. So I am exchanging gain for bandwidth, and then I am moving pole from one frequency to a higher frequency. So technically speaking, the loop gain product is the same. Okay, so the pole is moved to high frequencies, the gain has been reduced, so the gain pole product, it remains the same. But, and there is a big but, remember that it is the low frequency loop gain that gives us the accuracy of the amplifier. So the loop gain at low frequencies decreases, and then we have that the accuracy of the amplifier also decreases. So I have to use this one with a lot of care, and it will not be the first of our choices when we need to compensate an amplifier. We may only use this when we have a lot of loop gain. Okay, so those are basically the compensation techniques that we will use, and in order of importance. The first one is that we will try to to compensate our amplifier using a phantom zero, because this one it has the least negative effect on our amplifier. Then if we cannot do that, then we will use pole splitting, that it is already entering in the null implementation and adding capacitor and resistance. And then we will be doing pole zero cancellation compensation or resistive broadband in that order. Now, until now, we have been analyzing the stability of our circuits considering the position of the poles on the zeros, and we have said that we will want to move these poles to Butterworth positions, and they have to be in the left hand side of the complex plane, and most of the cases that will be the technique that we're going to use. But you have to be aware that there are classic stability analysis that are very well known and used also, and it's very good that we study how they work if you have not done that before in previous courses. So let's take a look for a second to the closed loop gain. So we have studied the closed loop gain, and then this is the formula of closed loop gain, and we see that the problem of stability happens when the denominator here is equal to 0, then the system becomes unstable. So we're going to study the denominator here. These are complex numbers, so then we have that 1 minus a beta is equal to 0. Then we can see that the problem occurs when the loop gain is equal to 1. That means when it is 0 dBs, and when the argument or the phase is equal to minus 180 degrees. So when the loop gain is equal to 1 and the phase is 180 degrees, this means that the poles will be located here, and then the system will start to oscillate. Okay, so how can we study this situation? Then for this one we will need to study a plot of ADB, and then we will need to study its phase, and that is what we do now, the classical stability analysis using both the plots. So we study the loop gain in dBs, and then I have here an example with two poles. And then here in the black one we have the this is the loop gain curve, and then we have that we have pole 1 at 100 Hz and pole 2 at 100 kHz, and then we just analyze its phase. So we can see here that exactly under pole 1 the phase of the loop gain has shifted minus 45 degrees. It starts shifting 1 decade before at 10 Hz, and it finishes shifting to minus 90 degrees at around 10 times the pole frequency. Okay, so the first pole will contribute with minus 90 degrees, and then the second pole that comes at 100 kilohertz, it will start shifting frequency 1 decade before. So it will start shifting frequency here. It will shift to minus 135 degrees. So let's add in minus 45 degrees exactly under the pole. And then it will finish it around 10 times higher frequency, that is 1 megahertz, with minus 880 degrees. So if we take into consideration these observations, we have to analyze what happens when the loop gain is equal to 0 dBs. Then I take this point here that it is equal to 0 dBs. I check this frequency, and then I just go to the phase and see how much phase is available before we hit 90 degrees, because this is going to be the phase margin, this distance here. Okay, For stable systems, it is commonly that we need at least a minimum of 45 degrees. In practice, we will need more than 60 degrees because due to process voltage and temperature variations, we cannot guarantee that this is going to be 60 degrees is going to shift to lower or higher values during regular operations. So we typically design for around 60 degrees. So you have to be aware that there are tools for doing classic stability analysis in Cadence and in other simulators. We are going to see that in the example also. But we can also plot the phase of A beta. We are already doing that in our simulation setups. We are already getting the AB, so we can reuse that one and just check the phase of A beta. So we can add it very easily to our simulation setups in order to do classical stability analysis. Okay, so now we are going to move forward and analyze a two-stage voltage amplifier. We're going to do the asymptotic gain analysis on this stage. Then we're going to extract the poles. And then we're going to test the main compensation techniques that are available for us, the phantom zero compensation, pole splitting, and pole zero cancellation.